December 23rd, 1944, Vielsalm, Belgium. Oberleutnant Klaus Reinhardt stood beside his disabled Panther tank, examining a piece of shrapnel that had killed his radio operator. The metal fragment was smaller than his thumb. Jagged, traveling at such velocity, it had penetrated the tank's ventilation system and torn through Gefreiter Schmidt's throat before lodging in the radio equipment. Reinhardt had commanded Panther tanks for 18 months. He understood artillery. He'd survived Kursk, where Soviet guns fired for hours without pause. He'd endured Normandy, where American artillery seemed to predict German movements with uncanny accuracy. But this barrage, 3 hours ago, had been different. The shells hadn't impacted the ground. They'd detonated in the air 30 feet above his column, raining steel fragments straight down into positions that should have been protected. His Panther, worth over 100,000 Reichsmarks, represented 9 months of precision manufacturing at the MAN factory in Nuremberg. Krupp, steel armor, Maybach engine, 75mm gun, capable of destroying any Allied tank at 2,000 meters, the pride of German engineering. And it had been disabled by a shell fragment from a weapon he didn't understand, fired by gunners who never saw their target, hitting with precision that violated everything Reinhardt had learned about artillery warfare. He picked up another fragment from the snow. American markings, 75mm caliber. But something was wrong. The detonation pattern was impossible. Artillery shells exploded on impact with the ground or after a time delay. These shells had detonated at precise altitude above his column, turning the entire road into a kill zone where foxholes offered no protection and tank armor meant nothing against fragments falling from above. That morning, Reinhardt's company had consisted of 9 Panther tanks, veteran crews, moving to reinforce the German offensive toward the Meuse River. By afternoon, 3 Panthers were destroyed, 4 damaged, including his own. 42 men, dead or wounded, not from tank combat, not from air attack, from artillery that behaved like nothing he'd encountered in 5 years of war. An American prisoner, and captured during the morning's advance, watched Reinhardt examine the fragments. The young soldier, barely 20, wore a 1st Infantry Division patch. He'd been driving a supply truck when German infantry overran his position. Reinhardt spoke adequate English, learned during peacetime engineering studies. "Your artillery," Reinhardt said, holding up the fragment. "These shells detonate in air." "How?" The American's expression shifted from fear to something approaching pride. "Proximity fuse, sir. They got radar inside, detects when the shell's near something and blows it up automatically." Reinhardt stared at him. Radar inside an artillery shell. Impossible. Radar equipment filled entire rooms. The Würzburg radar arrays defending Germany required trucks to transport, crews of specialists to operate. Radar sets were delicate, complex, required careful calibration. The acceleration forces of artillery firing would destroy any electronics instantly. When a 75mm shell fired, it experienced 20,000 times the force of gravity. Nothing electronic could survive that. "You're lying," Reinhardt said. The American shook his head. "No, sir. Been using them since June against the V1s. Every artillery unit's got them now. Cost about $10 per shell, I heard." "Maybe less." $10! Reinhardt's Panther cost 100,000 Reichsmarks, roughly 40,000 American dollars. And this American soldier claimed a $10 shell, mass-produced, containing miniature radar, had just disabled a tank that represented Germany's finest military technology. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. For the first time since Stalingrad, Klaus Reinhardt felt something close to despair. Not from casualties, not from tactical defeat, but from the realization that Germany was fighting an enemy who could put radar into artillery shells, manufacture them by the hundreds of thousands, and deploy them so casually that common soldiers discussed them as routine equipment. This is the story of how that impossible weapon was created, how it remained secret for 3 years, and how it revealed the fatal gap between German engineering perfectionism and American industrial pragmatism that would determine the war's outcome. The problem began long before Reinhardt's column was ambushed in the Ardennes. It started in the 1920s when military theorists recognized that aircraft were becoming faster, flying higher, and would soon be impossible to hit with traditional anti-aircraft methods. Anti-aircraft guns in World War I fired shells with mechanical time fuses. Gunners estimated the altitude of enemy aircraft, calculated how long the shell would take to reach that altitude, and set a small clockwork mechanism inside the fuse to detonate after a specific number of seconds. The system required extraordinary skill. Gunners had to judge aircraft altitude, visually estimate its speed and direction, calculate the shell's trajectory accounting for wind and atmospheric conditions, set the fuse mechanism with small tools while under stress, and load and fire before the aircraft moved out of range. Even under ideal conditions, accuracy was terrible. Studies from the 1920s showed that anti-aircraft guns required an average of 1,500 shells to destroy a single aircraft. In combat conditions, with multiple aircraft maneuvering at high speed, the ratio often exceeded 3,000 shells per kill. The mathematics were brutal. If defending a city required shooting down 50 aircraft per raid, and each kill required 2,000 shells, defenders needed 100,000 shells per raid. At peacetime costs of approximately $5 per shell, that was $500,000 in ammunition to stop one air raid. The system wasn't sustainable. Worse, as aircraft improved, the problem intensified. In 1920, aircraft flew at 100 miles per hour at altitudes of 10,000 feet. By 1935, modern bombers flew at 250 miles per hour at 20,000 feet. Fighters were even faster. Time fuses became increasingly useless. By the time a shell reached altitude, the target aircraft had moved hundreds of yards from where gunners aimed. The solution seemed obvious. Instead of time fuses, use proximity fuses. Create shells that detected when they passed near aircraft and detonated automatically. The concept was simple. The engineering was impossible. Multiple nations explored proximity fuses during the 1930s. Germany, Britain, France, the Soviet Union, and the United States all funded research programs. Every program encountered the same fundamental problems. First, detection mechanism. The fuse needed to sense when it was near a target. Possible methods included acoustic detection, listening for engine noise, photoelectric cells, detecting changes in light, electrostatic field detection, sensing the electrical charge difference between aircraft and surrounding air, or radio frequency detection using reflected radio waves. Each method had severe limitations. Acoustic detection was defeated by wind noise during shell flight. Photoelectric cells couldn't work at night or in clouds. Electrostatic detection had extremely short range. Radio frequency detection seemed most promising, but required miniature transmitters and receivers small enough to fit inside a shell nose. Second, survivability. Any electronics inside the shell had to survive forces that destroyed conventional equipment instantly. A 75mm shell fired from a standard American artillery piece accelerated from 0 to 2,800 feet per second in the 3-foot length of the gun barrel. That created acceleration forces of 20,000 G. Simultaneously, rifling grooves in the barrel spun the shell at 25,000 revolutions per minute for stability in flight. Standard vacuum tubes, the electronic components of the 1930s, shattered under these forces. The glass envelopes cracked, internal elements broke loose, connections failed. German scientists tested ruggedized vacuum tubes repeatedly during the 1930s. Every design failed. In 1943, German weapons development concluded that building a radio frequency proximity fuse for artillery shells was technologically impossible given current vacuum tube technology. Third, reliability and safety. The fuse had to remain completely inert during handling, transportation, and loading. It couldn't arm until the shell had traveled far enough from the gun to protect friendly forces. It needed to function in rain, snow, extreme heat, Arctic cold, and at any altitude from sea level to 20,000 feet. It had to be simple enough for ordinary soldiers to handle safely without specialized training. And it had to be cheap enough to manufacture by the millions. The British made the most progress before 1940. Researchers at Pi Limited developed ruggedized vacuum tubes for proximity fuses in unguided rockets. Rockets had relatively gentle acceleration compared to artillery shells, so electronics faced less stress. By mid-1940, British proximity fuses worked adequately in rockets, but failed consistently when adapted for high-velocity artillery. In August 1940, a British technical mission led by Henry Tizard arrived in Washington, carrying Britain's most secret military technologies. Among the items in the mission's black metal deed box were circuit diagrams and prototypes of British proximity fuse designs. The British hoped American industrial capacity could solve manufacturing problems they couldn't overcome alone. The National Defense Research Committee assigned the project to Section T of the Department of Terrestrial Magnetism at the Carnegie Institution. Section T was led by Dr. Merle Tuve, a physicist who had helped develop the theoretical foundations for radar in the 1920s. Tuve understood that the core challenge wasn't the concept, but the execution. Radio proximity fuses were conceptually simple. A miniature transmitter in the shell's nose emitted radio waves. When those waves reflected off nearby targets, a receiver circuit detected the reflected signal and triggered a detonator. Simple concept, extraordinarily difficult engineering. Tuve assembled a team of physicists and engineers with an impossible deadline. The Navy needed working proximity fuses for 5-inch anti-aircraft guns as soon as possible. Japanese air power was destroying American ships in the Pacific. Without effective anti-aircraft defense, the Navy couldn't operate. Tuve's team had months, not years, to solve problems that had stumped German and British scientists for a decade. The team included some of America's brightest technical minds. Richard Roberts and Henry Porter conducted circuit design experiments. Robert Broad worked on receiver sensitivity. Harry Diamond and Wilbur Hinman from the National Bureau of Standards developed fuse designs for rockets and bombs. The collaboration brought together academic researchers, government scientists, and industrial engineers in unprecedented ways. The first breakthrough came from Lloyd Berkener, one of Tuve's engineers. Berkener developed a system using separate transmitter and receiver circuits instead of a combined transceiver. This simplified the electronics and improved reliability, but the vacuum tube problem remained unsolved. Standard tubes shattered under artillery acceleration. The glass envelopes cracked, filaments broke, internal elements came loose and destroyed circuits. The solution came from an unexpected source. Western Electric Company and Raytheon manufactured miniature vacuum tubes for hearing aids. Hearing aid tubes were already ruggedized for portable use. They were small, mechanically robust, and used relatively little power. Working with Tuve's specifications, Western Electric and Raytheon engineers modified hearing aid tube designs to survive artillery firing. They reinforced glass envelopes. They redesigned filament mounts. They tested tubes by firing them from air cannons into solid blocks of wood, subjecting them to acceleration forces exceeding actual combat conditions. Most tubes failed. Engineers redesigned them, tested again, failed again, redesigned again. By January 1942, after months of iterative testing, they had vacuum tubes that survived 20,000 G-forces and 25,000 RPM spin rates. The tubes were tiny, barely larger than rifle cartridges. Each proximity fuse required 5 of these miniature tubes, along with resistors, capacitors, a battery, safety mechanisms, and a detonator, all packed into space smaller than a beer can, weighing less than 2 pounds. The battery system presented enormous challenges. Standard batteries couldn't withstand firing shock. Engineers developed a reserve battery activated by the setback force of firing. A small glass ampule containing electrolyte shattered when the shell fired, activating the battery only after the shell left the gun barrel. Safety mechanisms required equally innovative solutions. The fuse needed to remain completely inert during handling and loading. It couldn't arm until the shell traveled far enough from the gun to protect friendly forces. Engineers designed a complex system using mercury switches that required centrifugal force from the shell's rotation to close, combined with timers ensuring at least 0.3 of a second elapsed after firing before the fuse could detonate. This meant shells traveled at least 750 feet from guns before becoming active. In early August 1942, the Navy conducted the first live fire test in Chesapeake Bay. The cruiser USS Cleveland fired at radio-controlled drone aircraft on August 12th during its shakedown cruise. The test was scheduled for 2 days. It ended after 1 day because all drones were destroyed. Gun crews aboard Cleveland fired 4 shells. 3 drones were destroyed. Navy observers were astonished. The proximity fuses worked perfectly. For the first time in history, anti-aircraft gunners could reliably hit moving aerial targets without direct hits. Shells just needed to pass within 70 feet of targets, and proximity fuses would detonate automatically, shredding targets with shrapnel. The improvement over time fuses was so dramatic that some Navy officers initially suspected the test had been rigged, but subsequent tests confirmed the findings. The proximity fuse represented a genuine breakthrough, but successful testing and combat deployment were different things. Tuve's team needed to scale from prototype production to mass manufacturing. By January 1943, Section T had moved to a much larger facility and been reorganized as the Applied Physics Laboratory under Johns Hopkins University. The project now involved 26 contractors and 10,000 workers. More than 100 American companies contributed to proximity fuse production, including General Electric, RCA, Raytheon, Sylvania, Westinghouse, Eastman Kodak, Zenith, and Philco. Each proximity fuse contained 130 miniaturized electronic components. Assembly required precision work. Workers at factories across America built these fuses without knowing what they were building. Security was absolute. The project had the same classification level as the Manhattan Project. Workers who asked what the fuses were for were told only that they were critical to winning the war. The Crosley Corporation in Cincinnati became one of the largest manufacturers, producing 5.2 million units, roughly 24% of total wartime production. The company converted its player piano factory into a fuse assembly line. General Electric's Christmas tree lamp factory in Cleveland was retooled to produce miniature vacuum tubes. At peak production, American factories manufactured more than 100,000 proximity fuses per week. Fuses that cost $732 each in early 1942 cost just $18 each by 1945. That price reduction reflected improved manufacturing efficiency and economies of scale that only American industry could achieve. In November 1942, the Navy shipped 5,000 proximity fuses to Pearl Harbor. The Pacific Fleet received 4,500 of them and began distributing them to ships operating in the Solomon Islands. But fuses came with strict restrictions. They could only be used over open water where dud shells would sink. If a fuse failed to detonate and fell on land, Japanese engineers might recover it and reverse engineer the technology. On January 5th, 1943, those restrictions were tested. The light cruiser USS Helena was operating off Cape Hunter on Guadalcanal's south coast when Japanese dive bombers attacked. After dropping bombs, aircraft pulled up and began climbing away. Lieutenant Red Cochran commanded Helena's aft 5-inch battery. He ordered gun crews to fire 3 salvos with proximity-fused shells at departing aircraft. Gun crews had minimal time to aim. The aircraft was already several thousand feet away and climbing fast. All 3 shells exploded in air near the dive bomber. The aircraft disintegrated and fell into the ocean. Helena's crew had achieved the first confirmed kill of an enemy aircraft using proximity-fused shells in combat. It wasn't luck. It was repeatable technology. Over the next 12 months, proximity fuse effectiveness in naval combat became undeniable. In 1943, Navy ships fired 9,128 proximity-fused rounds and destroyed 61 enemy aircraft. That was 1 kill for every 155 shells fired. Old-time fused shells required 508 rounds per kill. the proximity fuse was more than 3 times as effective. By 1944, the number of proximity fused rounds fired climbed to 32,826, accounting for hundreds of aircraft destroyed. During the Marianas Campaign, proximity-fused 5-inch shells provided critical air defense for carrier task forces operating deep in Japanese-controlled waters. During the Battle of the Philippine Sea in June 1944, American ships equipped with proximity fuses shot down numerous Japanese aircraft attempting to attack carriers. Japanese naval aviators, among the most experienced in their fleet, found themselves unable to penetrate defensive screens created by proximity-fused anti-aircraft fire. One Navy study concluded that 5-inch guns previously needed approximately 1,000 time-fused shells to destroy one enemy plane. With proximity fuses, that number dropped to about 250 shells per kill, a 4-fold improvement. On May 11, 1945, the destroyer USS Hugh W. Hadley was on radar picket duty off Okinawa when more than 100 Japanese aircraft attacked in coordinated strikes. Hadley's 5-inch guns were equipped with proximity fuses. In 90 minutes of continuous combat, Hadley shot down 23 aircraft, setting an all-time U.S. Navy record for a single engagement. Every proximity-fused shell that came within 70 feet of targets detonated automatically, filling the sky with lethal shrapnel patterns aircraft couldn't avoid. But while the Navy was using proximity fuses extensively in the Pacific, the Army was prohibited from using them over land in Europe. The restriction remained in place through 1943 and most of 1944. Army artillery officers knew proximity fuses existed. They'd heard reports from the Pacific. They knew the technology worked. But Pentagon officials feared that even a single dud shell falling into German hands could compromise Allied advantages. Germany had the most advanced scientific establishment of any Axis power. If German engineers reverse-engineered the proximity fuse, they might develop countermeasures that could blind Allied radar or create their own proximity-fused anti-aircraft shells that would devastate Allied bomber formations over Germany. The risk seemed too great. That calculation changed on June 12, 1944. Germany began launching V-1 cruise missiles at London. The V-1s were jet-propelled flying bombs, pilotless aircraft packed with explosives aimed at civilian targets. They flew low and fast, approaching speeds of 400 miles per hour. They were extremely difficult to intercept. Traditional anti-aircraft guns rarely hit them because V-1s were too small and too fast for accurate time fusing. British fighter pilots tried to shoot them down or tip their wings to send them off course, but it was dangerous work. Many pilots died attempting it. The V-1s killed tens of thousands of civilians and caused massive damage to London. The Pentagon authorized limited use of proximity fuses to defend London on June 12, 1944. Initially, fuses were restricted to 90mm anti-aircraft guns and British 3.7-inch guns positioned along the English coast, where dud shells would fall into the ocean. The results were immediate and dramatic. In the first week of operations, British anti-aircraft guns destroyed 17% of incoming V-1s. This was already better than the 24% success rate achieved with traditional methods, including fighter interceptions and anti-aircraft fire combined. But as gun crews gained experience and fire control radars improved, the success rate climbed steadily. By the end of the 4th week, proximity-fused shells were accounting for 79% of all V-1s destroyed by anti-aircraft fire. By late August, after proximity fuses were widely deployed across the entire defensive belt, that percentage reached 74% of all incoming missiles. On some days, it reached 82%. The Germans launched 9,300 V-1s at England between June and August. Without proximity fuses, the casualties and destruction would have been catastrophic. British Prime Minister Winston Churchill later called the proximity fuse potent against small unmanned aircraft and credited it with preventing far greater loss of life. When V-1 attacks shifted to the port of Antwerp in September 1944, restrictions on proximity fuse use over land loosened further. Antwerp was critical for supplying Allied armies advancing into Germany. Losing the port would stall the Allied offensive. Germans recognized Antwerp's strategic importance and redirected remaining V-1 launchers to target the city and port facilities. Between October 1944 and March 1945, Germans launched more than 8,000 V-1s at Antwerp. British and American anti-aircraft units established defensive belts around the city. Once proximity fuses were deployed, a single anti-aircraft unit in Antwerp destroyed 48 of the first 75 V-1s they encountered, a 64% success rate. The port of Antwerp remained open for the duration of the war. On October 25, 1944, the combined Chiefs of Staff authorized general use of proximity fuses over land for anti-aircraft defense, formalizing what had become standard practice. But ground artillery still couldn't use proximity fuses against enemy troops. Army artillery officers were furious. They knew proximity fuses would be devastatingly effective against ground targets. A conventional artillery shell detonated on impact with the ground, which meant troops in trenches, foxholes, or behind cover were protected. But a shell that detonated in air above them would spray shrapnel downward into their positions. Trenches became death traps. Foxholes offered no safety. Even log-reinforced bunkers could be penetrated by high-velocity fragments. Proximity-fused artillery would multiply American firepower lethality many times over. But the Pentagon held firm. The risk of a dud shell falling into German hands was still considered too high. Army artillery would have to wait. Then, at 05:30 on December 16, 1944, Germany launched Operation Watch on the Rhine. 3 German armies attacked through the Ardennes forest in Belgium and Luxembourg, hitting thinly held American positions with overwhelming force. The attack achieved complete surprise. German armor punched through American lines and began driving west toward the Meuse River and Antwerp. The Battle of the Bulge had begun, and American forces were in serious trouble. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Colonel Oscar Alfred Axelson made his decision to use proximity fuses within minutes of the attack beginning. His 406th Field Artillery Group had just received shipments of posset shells, the Army code name for proximity fused artillery rounds. When the 38th Cavalry Squadron called for fire support, Axelson knew conventional shells would have limited effectiveness against German infantry advancing through forested terrain, but proximity fused shells detonating above trees would kill anything in the open. He ordered his gunners to load posset and fire. The effect was immediate and devastating. German infantry, caught in the barrage, were cut down by airbursts they never saw coming. The attack on the 38th Cavalry Squadron collapsed. 3 days later, on December 19th, General Dwight Eisenhower formally requested authorization to use proximity-fused artillery shells across the entire European theater. The German offensive was the largest attack the U.S. Army had ever faced. Every advantage mattered. On December 21st, all restrictions were lifted. Proximity-fused artillery shells were released for general use. The timing was critical. SS Colonel Otto Skorzeny's troops were attacking the town of Malmedy. American artillery battalions supporting Malmedy fired proximity fuses with devastating effect. Attacking German soldiers found themselves caught in airbursts that detonated overhead with no warning. Some Germans charged directly into artillery fire, hands raised, screaming, "Kamerad," trying to surrender. By December 23rd, estimates suggested as many as 2,000 German soldiers had been killed by proximity-fused artillery shells in just the first few days of their use. Germans quickly realized they were facing a new type of weapon. Prisoners of war repeatedly described the demoralizing effect of artillery shells that exploded in air above them with perfect timing. Traditional artillery gave soldiers a brief moment of hope, They would hear the whistle of incoming shells and dive for cover. If they were in trenches or foxholes, they might survive even direct hits nearby because explosions were on the surface. But proximity, fused shells, detonated 30 to 50 feet in air directly above defensive positions. There was no cover. There was no warning. Shells arrived silently at high velocity and detonated overhead, raining shrapnel straight down. Soldiers who had felt safe in prepared defensive positions were being killed without ever seeing the threat. The psychological impact was severe. This brings us back to Oberleutnant Klaus Reinhardt standing beside his disabled Panther on December 23, 1944, examining fragments and listening to an American prisoner explain that radar-equipped shells costing $10 had just crippled a tank worth $40,000. Reinhardt's military education had been thorough. He'd studied at the Panzer school in Munster. He understood combined arms tactics, fire and maneuver, concentration of force. But his education had been based on assumptions that no longer held, assumptions that German technology was superior, that German engineering would produce weapons the Allies couldn't match, that quality would defeat quantity. The proximity fuse violated all those assumptions. It wasn't superior technology. It was adequate technology, mass-produced, distributed so widely that even common soldiers discussed it casually. The American prisoner wasn't exaggerating about cost. Post-war records would show that by late 1944, proximity fuses cost between $10 and $18 per unit, depending on the model. Reinhardt's Panther, by comparison, required 1,200 man-hours to assemble. Krupp, steel armor plate, Maybach engine, precision optics, specialized ammunition. The tank cost 111,800 Reichsmarks, approximately 44,700 American dollars at official exchange rates. For the cost of one Panther tank, American factories could produce between 2,500 and 4,500 proximity fuses, and America was producing Panther's equivalents. The Sherman tank, at rates Germany couldn't match, while simultaneously producing proximity fuses by the millions. German commanders offered rewards for any soldier who could recover an intact proximity fuse. They needed to understand how the weapon worked so they could develop countermeasures or copy the technology. In late December 1944, German forces captured an American ammunition dump containing 20,000 proximity-fused artillery shells. German engineers examined the fuses carefully. They recognized sophisticated electronics were involved, but they couldn't understand how the technology worked. Most critically, German engineers couldn't believe that miniature vacuum tubes could survive artillery acceleration forces. Their own research had convinced them such tubes were impossible to manufacture. They assumed captured fuses were defective or designed for different applications. This was Germany's fatal blind spot. German engineering culture demanded perfection. When German scientists concluded that ruggedized vacuum tubes couldn't be built with existing technology, they stopped trying. American engineers working under wartime pressure with clear military requirements didn't have the luxury of theoretical certainty. They had to make it work, so they tested, failed, redesigned, tested again, failed again, and kept iterating until they succeeded. On the night of December 25th and 26th, 1944, General George Patton's Third Army caught a German battalion attempting to cross the Sauer River near Echternach, Luxembourg. American artillery units fired concentrated barrages using proximity-fused shells. The shells detonated above the river, and German troops massed on the banks. There was no cover on the riverbank, no place to hide. German soldiers were completely exposed in the open. Patton wrote a letter to the War Department describing the result. "The new shell with the funny fuse is devastating. We caught a German battalion trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think when all armies get this shell, we will have to devise some new method of warfare. I'm glad you all thought of it first." 702 confirmed German dead in a single artillery barrage. That was unprecedented lethality. Conventional artillery shells might have killed 50 or 60 soldiers under similar circumstances. The proximity fuse had multiplied American artillery effectiveness by more than 10 times, and this wasn't an isolated incident. Throughout the Battle of the Bulge, proximity-fused artillery devastated German formations caught in the open. In the Hürtgen Forest, an American chief ordnance officer reported finding 96 bodies from a German patrol hit by a massed proximity-fused artillery barrage. The bodies looked as if they had gone through a meat grinder, he wrote in his report. The high-velocity artillery shells arrived too quickly for German soldiers to hear them coming. Airbursts detonated with no warning. Foxholes provided no protection. Shrapnel even penetrated log-reinforced bunkers that would have stopped conventional artillery. German units that tried to advance through artillery fire were annihilated. German commanders reported that their soldiers were refusing orders to move forward because they knew proximity-fused artillery could kill them, even in covered positions. Prisoners of war interviewed after capture described being in dazed states after surviving proximity-fused barrages. They realized they were facing new kinds of artillery, but couldn't understand how it worked or how to evade it. Minor mutinies broke out among German units ordered into areas known to be covered by American artillery. Some German soldiers simply refused to leave bunkers when proximity-fused artillery was falling. Germans felt safe from traditional timed artillery because heavy overcast weather prevented accurate aerial observation. American forward observers couldn't see German positions clearly, which meant timed artillery shells would be set based on estimates that were often inaccurate. German troops had learned to take cover whenever they heard artillery fire and wait for barrages to end. But proximity-fused shells didn't require accurate observation. Fuses automatically detonated at optimal heights above ground, regardless of weather conditions or visibility. American gunners just needed to know approximate locations of German forces and fire. The proximity fuses did the rest. The bad weather that had protected German forces now meant nothing. By late January 1945, German resistance in the Ardennes had collapsed. The Battle of the Bulge was over. American forces had stopped the largest German offensive of the war and were preparing to cross the Rhine River into Germany. Proximity, fused artillery, had played a critical role in that victory. Patton later stated that the funny fuse won the Battle of the Bulge for us. While that was an overstatement, the proximity fuse had undeniably changed the tactical situation. German forces that would have been able to defend prepared positions effectively against conventional artillery were wiped out by airbursts they couldn't avoid. Klaus Reinhardt survived the Ardennes. His Panther was repaired and returned to service in early January 1945. But the experience had fundamentally changed his understanding of the war. Germany wasn't losing because German soldiers lacked courage. German soldiers were among the finest in the world. Germany wasn't losing because German tanks were inferior. The Panther was arguably the best medium tank of the war. Germany was losing because the United States could develop technologies like the proximity fuse, manufacture them by the millions, and deploy them so widely that they became routine equipment. Germany's industrial base, already strained by years of war and Allied bombing, couldn't compete on those terms. Reinhardt participated in Germany's retreat across the Rhine in March 1945. His Panther Company, which had started the Ardennes offensive with 9 tanks, was down to 3 operational vehicles by the time they reached German territory. 2 tanks were lost to proximity-fused artillery. 3 were destroyed by American tank destroyers. 1 was abandoned due to mechanical failure when spare parts weren't available. On April 11th, 1945, Reinhardt's Panther ran out of fuel near Jena. No fuel convoys arrived. The tank was disabled without firing a shot. Reinhardt and his crew surrendered to American forces 3 days later During post-war interrogation, American intelligence officers asked about the impact of proximity fuses on German tactics. Reinhardt's response, recorded in intelligence summaries, was direct. The proximity-fused artillery made defensive positions death traps. Previously, soldiers in foxholes or trenches had reasonable chance of survival during artillery barrages. After proximity fuses were introduced, there was no safe place. Soldiers knew they could be killed by shells exploding above them, even in deep positions. This destroyed morale and made defensive operations nearly impossible. The final statistics tell the complete story. American proximity fuse production during World War II exceeded 22 million units. At peak production in early 1945, American factories manufactured more than 100,000 fuses per week. Unit cost, by war's end, was approximately $18 per fuse for the most common models. The United States expended approximately 5 million proximity-fused artillery shells in combat during the war. The Navy fired the majority, roughly 3 million rounds, primarily in anti-aircraft roles in the Pacific. The Army fired approximately 2 million rounds, mostly during the final 6 months of the war in Europe. Combat effectiveness data from U.S. Army Ordnance reports showed that proximity-fused artillery was approximately 3 to 4 times more effective than conventional artillery against personnel in the open. Against vehicles and equipment, effectiveness improved by factors of 5 to 10 times because air bursts distributed fragments over much wider areas than ground bursts. German casualties specifically attributed to proximity-fused artillery are impossible to calculate precisely, but American after-action reports from December 1944 through April 1945 consistently note that German prisoners described proximity-fused barrages as the most psychologically devastating weapon they encountered. Post-war interrogations of German officers revealed consistent assessments. Field Marshal Gerd von Rundstedt stated that American artillery superiority, particularly proximity-fused shells, made German defensive operations in the Ardennes impossible. General Hasso von Manteuffel acknowledged that proximity fuses negated traditional infantry defensive tactics based on foxholes and trenches. The proximity fuse demonstrated a pattern that repeated throughout World War II. Technological advantage in warfare didn't come primarily from theoretical breakthroughs. It came from engineering execution and manufacturing scale. The concept of proximity fuses was well understood by multiple nations before the war began. What separated success from failure was the ability to solve thousands of small engineering problems, manufacture components to precise tolerances, and produce complex electronic devices in quantities of millions while maintaining quality control. The United States had the industrial base, skilled workforce, and organizational structure that could coordinate work across dozens of contractors. Germany did not. By 1944, American industry was producing more proximity fuses every month than Germany had produced artillery shells of all types combined. General George Patton had been correct when he wrote that armies would need to devise new methods of warfare once proximity-fused artillery became widespread. The assumption that soldiers in trenches or foxholes were safe from artillery fire had been fundamental to military tactics since World War I. The proximity fuse shattered that assumption. Defensive positions, considered adequate protection against artillery, were now death traps. Armies would need to disperse more widely, dig deeper fortifications, and move faster to avoid artillery barrages. The tactical changes forced by proximity fused artillery rippled through military doctrine for decades. Modern artillery doctrine still emphasizes airburst munitions as standard, not specialized ammunition. The GPS-guided artillery shells used in current conflicts routinely include airburst fusing options descended directly from the World War II proximity fuse. Dr. Merle Tuve never received public recognition for leading proximity fuse development during the war. The project remained classified until after Japan surrendered. Even after the war ended, Tuve was reluctant to discuss his role. He understood that Section T had solved an engineering problem that saved thousands of Allied lives, but he also knew that many people at many organizations had contributed to that success. The proximity fuse wasn't the work of a single genius. It was the product of systematic collaboration between physicists, engineers, manufacturers, and military personnel across dozens of organizations. Over 22 million proximity fuses were produced during World War II by more than 100 manufacturers. That scale of production required contributions from thousands of people, most of whom never knew what they were building. After the war, Tuve returned to the Department of Terrestrial Magnetism at the Carnegie Institution and served as its director from 1946 to 1966. He continued research in geophysics and radio astronomy. In 1948, he was named an honorary commander of the Order of the British Empire for his service to the Allied cause. President Harry Truman awarded him the Presidential Medal for Merit. But Tuve rarely spoke about the proximity fuse. When asked about his wartime work, he emphasized the collaborative nature of the project and the contributions of engineers and technicians who had solved countless technical problems that made mass production possible. Dr. Merle Tuve died on May 20th, 1982, at the age of 80. His obituaries mentioned his contributions to geophysics and his leadership of the Applied Physics Laboratory during World War II, but most didn't detail the specific work he'd done on proximity fuses. The technology had been declassified for decades, but it remained obscure outside military and technical circles. Tuve himself had never sought publicity for his wartime work. The Applied Physics Laboratory that Tuve founded continues to operate today as a research facility of Johns Hopkins University. It conducts work in national security, space exploration, and advanced technology development. The building in Silver Spring, Maryland, where Section T first assembled proximity fuses in 1942, no longer stands. It was demolished decades ago and replaced by commercial development. There is no memorial marker at the site. The workers who assembled proximity fuses in factories across America went back to their peacetime jobs when the war ended. Most never learned exactly what they'd been building. The soldiers and sailors who benefited from proximity fused ammunition rarely knew the technical details of how fuses worked. They just knew that anti-aircraft guns were suddenly much more effective and artillery barrages were far more lethal. The 702 German soldiers killed by proximity fused artillery on the banks of the Sauer River in December 1944 were buried in military cemeteries in Luxembourg and Germany. Their graves don't mention how they died. Military records list them as killed in action by artillery fire, which was true, but incomplete. They were among the first ground troops anywhere to be killed by technology their own scientists had declared impossible. They died, not knowing that shells exploding above them contained miniature radar sets more sophisticated than anything Germany had been able to build. They died, not knowing that American factories were producing these shells by the hundreds of thousands, while German industry struggled to manufacture basic artillery ammunition. The German engineers who had declared proximity fuses impossible never understood what they'd missed. After the war, American technical intelligence teams interrogated German scientists and showed them captured German documents detailing their proximity fuse research. Germans had explored most of the same technical approaches that Section T had used. They'd considered radio frequency fuses, vacuum tube designs, and miniaturization techniques, but they'd concluded that engineering challenges couldn't be overcome with existing technology. What separated the American project from the German project wasn't a difference in scientific knowledge, but a difference in engineering persistence and manufacturing capability. American industry could produce miniature, ruggedized vacuum tubes in quantities of millions. American engineers could iterate through dozens of design failures until they found solutions that worked. Germany lacked the industrial base and the time to compete on those terms. This is how wars are actually won, not through dramatic breakthroughs or genius inventors working in isolation, but through systematic collaboration between scientists, engineers, manufacturers, and military personnel. The proximity fuse succeeded because Section T could draw on resources of American industry, technical expertise of academic researchers, and practical knowledge of Navy ordnance officers who understood what combat conditions would demand. It succeeded because Western Electric and Raytheon could manufacture ruggedized vacuum tubes that no one had built before. It succeeded because factory workers across America could assemble complex electronics at scales that would have been impossible for any other nation. And it succeeded because Colonel Oscar Alfred Axelson made the decision to use the technology when it mattered most, even though he was violating direct orders by doing so. The story of the proximity fuse is the story of American industrial and scientific power at its peak. It's the story of what becomes possible when brilliant people are given clear objectives, adequate resources, and freedom from bureaucratic constraints. It's the story of innovation that happens not through individual genius, but through systematic problem-solving at scale. And it's the story of technology that saved thousands of Allied lives and changed warfare forever, developed by people whose names are mostly forgotten today. Oberleutnant Klaus Reinhardt lived until 2003. He settled in Bavaria after the war, worked as a mechanical engineer, rarely spoke about his wartime experiences. In a 1998 interview for a German documentary about armored warfare, he was asked what moment during the war made him realize Germany would lose. His answer was immediate. December 23, 1944, when an American prisoner told me they'd put radar inside artillery shells and were making them for $10 each. At that moment, I understood we were fighting an industrial power we couldn't match, not because American soldiers were better, not because American tanks were superior, but because America could make the impossible routine. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.